Year 8, Energy Reverse the Classroom. Now this is a fairly big topic, right? So there's a lot of information and a lot of words that then you need to know within the energy topic itself. Right. This is the snaky diagram. Right. So what we're going to be doing is we're going to be talking about energy and foods, energy stores, energy and temperature, particles, waves, energy resources. There's a few little calculations involved, including power and work done. There's a fair bit in it. Now this is then a practical that you've done previously, right, in the health and lifestyle. Now this is talking about where you burn a food, right, what you do is you put it on the end of a needle, set fire to the food on the end of the needle, and then energy transfers into the water. What you can do different types of food to give you an idea about which food has got the most energy in it. Now, from a purely scientific point of view, it's a terrible experiment because so much energy is just lost to the sides, right? But it does give you a little bit of an idea about what's going on and which food has got the most energy. These are then the energy stores, and I've got to be honest, you've just got to know them, all right? So this is where energy is stored. Magnet and electric, thermal, chemical, kinetic, gravitational, nuclear, vibrational, and elastic. You just need to go away and you just need to remember them, right? They need to be kind of listed and you need to be able to regurgitate them. Then once you've got the actual energy stores, what they are is they are then in one form and they are transferred to something else. And these are then called the HERM. So HERM. And they are heating, electrical, radiation and mechanical. So heating is all to do with temperature. And what it can be done, it can be transferred by conduction, convection and radiation. Electrical transfer of energy, it goes from a power source such as a cell, and what it is then delivered to something else. Radiation is light and sound, and what they do is they carry energy between 2 points. And the final one is mechanical, is when there's a force acting on something. So for example, a collision. Now, conservation of energy. The principle of conservation of energy is the amount of energy always stays the same. So if I've got like a little train and it's got high potential energy, low kinetic energy, I let go of it and what happens is it rolls down the hill. Right, then it goes up on another side, but what you've got to remember is energy is conserved. So you've got exactly the same amount of energy in the system as you had at the start. Now some of it might be lost, right, or changed into another store, like there might be sound given off, which is where energy is then lost from this individual system. Dissipate. Here's a good word. Dissipate is to scatter in all directions or to use wastefully. So if you've got a Bunsen burner going, what you're doing is you're dissipating out the heat. A pendulum. Describe how the gravitational store of energy and the store of kinetic energy changes with the pendulum. So what it does, it starts up here and it's got a lot of gravity. Okay, because what it is, it's away from gravity. And because it's stationary, it's got no kinetic. When I let go of it, that gravitational turns into kinetic energy. When it gets to the bottom, there's more gravitational energy turned back into kinetic, right? In fact, it's kind of the maximum. Then what happens is, as it starts going back up the other way, the kinetic energy then starts to become gravitational energy until it stops again, where you've got your maximum amount of gravitational energy. Temperature. Temperature is a measure of the average energy of the particles in the material. The faster they are going, the hotter they are. Now this is then 3 ways of heat transfer. We've got conduction, convection and radiation. So what we can do is conduction is when you have direct contact. So if you've got a metal saucepan, like I see in the diagram there, and you touch it, the heat is then transferred to you by conduction. Convection, I always call it heat rises. Right, so if you put a hand over the top of a radiator, what you'll find is it's warmer, and that's because of convection. if I heat something up like I'm doing in that diagram there, what happens is the hot liquid rises to the top, and eventually what it does, it kind of spins around because then it cools down. And radiation is where energy is transferred by an electromagnetic radiation, which is like a wave of energy. So again, if you stand in front of a fire, what you can do is you can feel the energy coming towards you, which is then radiation. Now, how does a cup cool down? Think about conduction, convection, and radiation. So radiation is where the actual cup itself is giving out heat as a radioactive wave. Convection is where the heat is rising, and conduction is where the heat is then going through the base because there's a physical contact. So there's contact between the cup and the desk. Thermal radiation, right? Now, electricity generation. And again, what we're doing is we're going through huge, great big topics, and you've just got to understand exactly what's going on with each one. So we're going to start with a power station now, and what a power station does is it generates electricity. What it does is it burns the fuel. When it burns the fuel, what it does is it boils water, right? So that's supposed to be water, okay, and it's boiling, it's getting dead hot. That steam comes out, and what it then does is it spins a turbine. And a turbine, it looks a bit like like a propeller, right? A bit like you see like a wind turbine. It looks like one of those, but it can be inside something. That turbine spins a generator. That generator then makes voltage, which is then your electricity. Once that electricity is then made, it goes into the national grid, which takes electricity across the whole country. So it starts off in the power station, it goes to a step up, increased, so voltage, decreased, and here with a step up transformer, voltage is increased. And that makes it more efficient. Then what it does, it gets into your house and your factory. And in your house, we're talking about 230 volts. Now, this is then another diagram of electricity generation. What we have is we have heat energy that then spins a turbine, which then spins a generator, which then goes to a transformer and it gets sent across the country. Electricity from coal, what I'm going to do on these is I'm just going to very, very briefly just talk about exactly what's going on, but the best thing to do is kind of pause the videos and have a look at the sort of the information that's going on in it. So if I start here, we've got our boiler, which is where the coal is burning. It creates steam. Steam spins a turbine. The turbine spins a generator, and you make electricity. Nuclear power, everything's kind of working exactly the same. What we have here now is we've got our nuclear power plant here, which has kind of got the control rods in. Water's boiled. Water comes out as steam, steam spins a turbine, spins a generator, makes electricity. Hydroelectric power, again, it's kind of all working, they're very much the same. What we have at the top here is we have water. You open up a little sluice gate here, water goes flying down this tube here, spins a turbine, spins a generator, there's a turbine, spins a generator, and you make electricity. Tidal energy. What you've got on this top one here, this is then the tide coming in. So water comes in that direction, and when it goes under the barrage, because it can't go over the top of it, right, it goes under the barrage, and there's a turbine here. And you'll never guess what that's connected to. It's connected to a generator, which then makes your electricity. So that's the water then flowing in that direction. When the tide goes out, water then flows in the opposite direction. Makes the turbine spin, which spins the generator, which then makes electricity. Now this slide here, what it does, it's a big summary slide. And I'm not going to go through this, right? But what it does, it goes through all of the kind of the energy resources. It goes through how they work, their uses, but then the most important thing is the positives and the negatives. Because in the exam, what you could quite easily be asked about is positives and negatives of each of the energy sources. So what I suggest you do is I suggest you stop it, read through it all, and make some individual notes on it. Two equations that again you're going to be doing in this unit. We've got work. This is the equation. Work done equals force times distance moved. Work is in joules, force is in newtons, distance moved is in meters. Right? And what work is doing work transfers energy from one store to another. So what I'm doing at this moment, I'm talking. So I've then got energy in me, and then it's getting transferred to sound, and it's going elsewhere. Power is the rate of energy transfer. Now there's a couple of equations for that. Power equals energy transfer divided by time. Power is measured in watts, energy transfer in joules, time in second. And another one could be power equals work done divided by time, where power is measured in watts, work done measured in joules, time measured in seconds. And what you'll do in lessons is you'll go through sort of examples of each one of those, right? But if you're familiar with them already, then it's going to benefit you. Right, 5 questions. What is Herm? I want 4 words. Explain how electricity is made in HEP. I went through it very briefly. You need to explain in a paragraph. What make up the national grid? Let's we call it makes up the national grid. It's on a little diagram. Describe the energy changes in a pendulum. Start with gravitational, kinetic, etc., etc. What is the definition of conservation of energy? Now that energy topic is huge. But what you'll find is when you get into year 10 and 11, you're going to do the same sort of stuff again, but if you know it now, then all it's going to do is benefit you.